Dinner good, Kevin?
I'm still eating it.
Oh, there you go. Good for you. Okay, now where am I going? What am I doing? Oh, yeah. Just got to get the, this shouldn't take us long tonight.
All right, football's on, so
Uh-huh. Football's on is Tuesday.
I know they got rescheduled because of COVID.
Oh, amazing. Okay, we seeing this or not yet? We're not seeing the slideshow yet, are we?
No.
Okay, now you're seeing it, right?
Yeah.
Finest kind. That last lab report was a train wreck, guys.
Yes.
All you had to do was look and see that when you put the stuff in with the chlorine, when you turned the B minus into the chlorine, it turned an orange color. That indicated that it was bromine, guys. So the actual answer was magnesium bromide. And that was what really told you what the final answer was. What can I tell you? So how did you do on it?
I got the magnesium part right.
Okay.
Yeah, that's the only part I think I got right. I got a 76 or something.
That's not bad. Hey, some people got worse than that because they weren't, they didn't give me the description I wanted. So they didn't even get credit for that. So up in the air. And a lot of the people didn't show up to the Zoom meeting. So they got literally looking at those videos. I was disappointed in the videos. I really thought that they would go into more detail with them, and they didn't. And it kind of threw you off, and I know it did because they didn't show you taking bromide and putting it with bromine to show you that you get the orange color. So that
I thought that was weird.
all you were seeing was no reaction. You weren't seeing the actual color that the no reaction gave you. Does that make sense to you?
Yeah, that
Yeah.
makes sense.
So I can't blame you for that, but I'm in a hard place here, guys. Just know that one of these labs will be dropped and ultimately it's not going to kill you. All right, trust me. That's all I got to say. Just keep on trusting me. We'll get through it, all right?
Yes, sir.
I got 7 people in here. Are we all good, guys?
Yep.
I am really disappointed for a couple reasons. One of which is this is the most exciting lab that you would have had this semester. And it's really great because what you do is you fill up a tube with hydrochloric acid. And at the very one end of the tube, you stick a little ball of magnesium chloride in there. Then you flip it, throw it into a bucket, and literally speaking, this magnesium reacts right away, and you create a whole bunch of hydrogen in this tube. It really, really works wonderfully. And the other part is it's really, really accurate. So I'm sorry you're not going to be able to do this, but we'll go from there, all right? Bottom line, what happens is you have this copper wire. This copper wire basically sticks in the very bottom of this big, long tube. Now, the way you do it is you put 5 milliliters of concentrated hydrochloric acid in the very bottom, and you kind of layer. Has anybody ever done a layer drink? You know what I'm talking about with a layer drink?
Yeah, I understand, sir.
So you basically pour it. Now, because concentrated HCl has a larger density than dilute HCl, you're able to layer the dilute on top of it. So that when you flip this, the heavier hydrochloric acid goes down and attacks the magnesium and makes all these bubbles. The bubbles come up, they fill the very top of the tube, and it literally drives the level of the water down. So we are reacting magnesium with hydrochloric acid, and the gas we're producing is hydrogen. But we also have to remember that that hydrogen gas is collected over water. So we're going to have to accommodate the water vapor pressure in here as well. So if we're dealing with the ideal gas law, none of our parameters are changing. Pressure's not changing, temperature, or, well, the number of moles are changing, but eventually what happens is we stop the reaction, and when we stop the reaction, the moles are all gone. So the moles of HCl at that point are of H2 are constant. And the volume isn't really changing. The volume is what it is. But since we want our R factor in liter atmospheres per mole degree Kelvin, all the values we come up with need to be converted. The pressure needs to be converted to atmospheres, volume must be in liters, temperature in Kelvin, and obviously the moles must be in moles. All right, the parameters we have for this, what we measured. The reading, our very first thing, our reading of our burette was 41.50 milliliters. What we did, the first step of this reaction, the numbers on the tube we're using aren't accurate. So we have to convert the numbers in the UDO tube, the tube we're using, with actual values. The way we do this, we put a known value, a known volume into our burette. We put 41.50 milliliters into our burette. We drain that down. We put that amount of volume into the UDO tube, and we found out it measured at 44.0 milliliters. Okay? We did our experiment. We put our magnesium into our HCl. The hydrogen bubbled up, and the volume that was recorded by the UDO tube was 38.30. Our atmospheric pressure was 765 torr. Temperature was 26 degrees Celsius, and the water vapor pressure at 26 Celsius is 25.2 torr. We measured out 0.0331 grams of magnesium. This is all we measured out, ladies and gentlemen. Now we have to get the real pressure. We have to get the real volume. We have to get the real temperature, and we have to get the moles of hydrogen. So part of what we're doing is we need to find out what the pressure is inside of our tube. If the level of the liquid inside the tube is the same as the level outside the tube, then what you have is that the pressure outside isn't pushing this up, and the pressure inside isn't pushing this up. What that means is that the pressure inside the tube is the same as the pressure outside the tube. That makes sense to you, guys?
Yeah.
So
Yes, sir.
what you do is you move the tube up and down until you see the gas space. You see where the line is, where the liquid is in the UDO tube. You move that tube up and down until you get those two level. Once it's level, you know the pressure inside the tube is the same as the pressure outside the tube. That's when you take the volume. We moved our tube up and down, and we found that the reading on our UDO tube was 38.30 milliliters. All right. Now we got to figure out what our pressure is. All right. Okay. I told you the atmospheric pressure was 765. And I also told you that the pressure inside the tube was the same as the pressure outside. But the pressure inside the tube is equal to the pressure of the hydrogen and the pressure of the water. So if the total pressure is 765, then this 765 is equal to the pressure of the hydrogen plus the pressure of the water. Pressure of the water at 26 is 25.2 torr. I just simply subtract that from 765. This gives me 739.8 torr as the pressure of the hydrogen inside the tube. First step, take the barometric pressure, subtract the water vapor pressure away from it. That will give you the pressure in torr. You then convert it to atmospheres by 1 atmosphere over 760 torr. This gives us 0.9734 atmospheres. Are we good at this point?
Yes.
Okay. Next step, we got to deal with the volume. As I said, the UDO tube isn't nearly as accurate as our burette is. When we did the initial burette reading, that was 41.50 milliliters. When we emptied all of those 41.5 milliliters into the UDO tube, it measured 44.00 milliliters. So our fudge factor, we take our burette reading, divide it by the UDO reading, and that will give us a number. Now this is, if you want to think of it like this is 0.9432 milliliters burette, or in other words, accurate milliliters, divided by 1.00 UDO milliliters. If we have that term, then our UDO milliliters, which was what we measured by moving the tube up and down, if that was 38.30 milliliters, and I multiply that by 0.9430 accurate milliliters over UDO milliliters, I get 36.12 accurate milliliters. Then, because I need to convert it to liters, I multiply it by 1 over 1,000 milliliters. So I have 0.03612 liters. Temperature, straightforward conversion. I add 273.15 to 226.0. I get 299.2. Last thing, I have the weight of my magnesium. Okay. I also have a balanced chemical equation. Looking at the equation, I know stoichiometrically, if I have moles of magnesium, that gets converted 1-to-1 ratio into moles of H2. So all I got to do is take my grams of magnesium, divide that by the atomic weight of magnesium. This gives me my moles of magnesium, which equals my moles of H2. So my solution, my R is equal to my pressure times my volume divided by my moles times the temperature. I plug all the corrected values in there. I end up that my R value is 0.0864. Now we know what the true value is. True value for R is 0.0821. So in order to get a percent error of that, I take my real value minus my experimental, divided by my real value times 100. I do that math out and I get a 5% error approximately, which is fairly good.
I have a question.
Yep, I'm here, Dominica.
Okay, does R have units?
Yes, R has units. Those units are, okay, Dominica, if I use this number, 0.0821, then that means the units are liter atmospheres per degree Kelvin mole. Okay, Dominica?
Okay.
If I change those units, the number changes. When you
Okay.
go to Chem 2, you're going to be using another value for R, and that involves energy. And that value is going to be 8.31 joules per mole Kelvin. Okay? So if we use this value, 0.0821, then we have to put everything to liter atmospheres per degree Kelvin mole. Any other questions, guys? Then I make the motion that we adjourn until next Wednesday. Fairly simple lab. Kevin?
I thought we were supposed
Oh,
to use 0.08206.
But my answer, because of this value, Kevin, if this is the amount of
Yeah.
grams of magnesium, isn't that, when I plug that into this, isn't that going to limit my value of R for being three significant figures?
Oh, I guess if we're solving for R, but I don't see why it would limit that as using it as a base.
Repeat your question, Kevin. You threw
Like,
me one.
we're solving for R? Okay, I see. If it's a constant, we would use 0.08206, but if we're solving for it, we use sig figs.
Oh, yes. Yes.
Roger that. I got you.
Well, Kevin, that number goes out beyond 6, you know. It's 0.08206 something, 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 something.
Yeah,
It's
that's
just-
just all I've ever used.
Yeah, same here. I haven't gone out, mainly because what normally limits you is the, normally when you do these things, it's in 4 sig figs. Because generally speaking, balances go out to the 4th place. So moles are going to go out to the 4th place. When you add degrees centigrade and 273, that's going to be 4. Milliliters, burettes read out to the hundredths place, so they're going to be 4. And atmospheres is generally written out to the tenths of a millimeter, so that reads 4 as a general rule. So normally that's why that's the number, Kevin.
Cool. All right.
Normally
You have a good
speaking,
night.
all these numbers are 4 sig figs. It just so happens that when I did it this way because our balances only go out to the 4th decimal place. That means that that mass is only 3 sig figs. Okay?
Okay. You have a good night.
That was quick enough, Kevin. Enjoy the rest of your dinner.
All right.
I do have one question
I'm
real
here.
quick. So for the lab notebooks, I noticed there was 2 separate procedures. Did you want us to copy down both separate procedures or just the first one?
I'm sorry. Vanessa, I'm sorry. You absolutely threw me for a loop there. I know what you're talking about now. Use the concentrated HCl.
Okay, so I think
Both
that one
both
was-
procedures will work. You can use both procedures, but if you use the dilute procedure, it takes you forever and a day. If you use the concentrated one, then it goes really, really fast.
Okay, thank you.
Anything else, guys?
No.
So just to be clear, so to find the that final value, you take the
To find R?
to find R,
Mhm.
not R. When you find the what is it, the procedural error where you
The UDO tube?
yeah.
Okay. All right. The first step, who am I talking with, by the way?
This is
Ian?
Khalil Thompson.
I'm sorry, this is Khalil. Okay, Khalil. The first thing you do, if you look at the procedure, the first thing it tells you to do is to basically standardize your tube. Some of the people do this just using the burette itself. The Gibbs campus happens to have these tubes. These tubes work great, except they're not accurate. So the first thing you have to do is you have to standardize it. So what you do to standardize it is you take a known volume. I just use 41.50 to make it a little more interesting. Normally what you do is you fill the burette up to 0.00. You let it drain down to 10. So you have 40 milliliters and you're draining it right into the UDO tube. So those 40 milliliters are read by what the UDO tube reads. And whatever the UDO tube reads would be the reading for that. Now the fudge factor is you take the actual value that you know to be valid, the burette reading, divided by the UDO reading, and that will give you your fudge factor. You have to multiply the fudge factor by the reading of the UDO tube when you're actually doing the experiment, and that will give you the volume. That will give you the volume of the gas in the tube. Khalil, does that make sense to you now?
Yes, sir.
Okay. Anything else, Khalil, or anybody else?
I have a question about the extra credit for the normal class.
Okay.
So for part 1B, it asks how many or how much of AgCl was precipitated. Do you want that in grams? Is that what you mean?
Yes.
Because it doesn't specify. Okay. Thank you.
Thank you, Jasmina. I will have to write an email out tonight, right as we leave. I'll have to write an email saying I want all reported things to be in grams. Thank you.
All right, you're welcome.
Anything else, guys? Okay, I don't have anything more for you, so I'll see you next Wednesday then.
Cool.
Yes, sir.
Have a
Thank-
good one.
Thank you.
Take
All right,
care.
have a
Take
good
care.